Hello, my name is Bill McCarthy, and I'd like to demonstrate the workings of a 19th century steam-powered wood shop. In the 19th century, before the invention of electric motors, all shops and machinery would have been powered off of a central power source, whether it was steam or water. Behind me is a 6-horsepower horizontal steam engine, a bore and stroke of 4.5-inch bore and a 5-inch stroke. This engine originally came from a blacksmith shop up in the coal regions of Pennsylvania. Now, this engine requires a source of steam, and over here to my left is a 6-horsepower O&S vertical fire tube boiler. This particular boiler has a firebox down here, and in there the fire is built, and there are 22-inch diameter tubes which run vertically from the firebox up to the top to the smoke hood. And those tubes are surrounded by water, and the products of combustion, the flame, goes up through the tubes, heating the water. Now, in making steam, the ratio of water to steam is 1 gallon of water will make 1,700 gallons of steam. Basically, all you need is a vessel that can withstand the pressure and a source of heat. We are burning wood, but this boiler could have also been used with coal. Now, with steam and high pressure, safety is always an issue, and your boiler must be equipped with a safety valve and also a method of putting water back in the boiler. Over here on the right side of the boiler, you will see what's referred to as a sight glass. And in here, you can see what the level of the water is, which is right approximately here. Now, you have to keep your water level within this safe limit, and you cannot let it drop below. Now, over here, my hand is on what are called tricocks, and these are a method of making sure that your gauge glass isn't lying. Occasionally, gauge glasses can become plugged, and they'll give you a false reading. So what you do then is you will open your tricocks and you just crack them ever so small amount, and you'll see drips of water comes out. That means that the water level is above that. And we'll open this one up and see what happens here. And water also comes out of that one. So that means that our water level is above the tricocks and we're in the safe mode. Now on the back of the boiler, which you probably can't see, is a device called an injector. This is a device for putting water back in the boiler, because once your engine is running, you're using steam, and you need to replace water in the boiler to keep the water level in the safe zone. And this was invented by a Frenchman in the late 1850s, and the way this works is theoretically it shouldn't work, because you're using steam pressure in the boiler, and right now we have about 95 pounds of pressure, and you are applying that to a water source coming into the boiler, and you would have 95 pounds on either side, and basically your water wouldn't be going anywhere. However, due to some principles of physics, namely velocity and condensation, you gain a few extra pounds in order to push the water back in the boiler. And I'll operate this right now. I'm turning on the steam, and now, you can hear that sound it's making. That means the injector is working and putting water back in the boiler. And our water level is rising. We'll let that run for a little bit, and then we'll turn it off. Now, behind me is a steam engine, and in a minute or so I'll turn it on. But first, I'd like to talk about the power transmission system. You will see the steam engine has a flywheel here, and this steam engine operates at about 200 RPM. And what we will be doing is we'll be transferring the power from the steam engine through this belt up to a system of overhead shafts, which are typically referred to as line shafts. And through these line shafts, we will transmit power to individual machines through a clutch system and what's referred to as a countershaft. Now, the reason for the countershaft and the clutch system is you basically do not want to run all your machines all the time. You want to be able to selectively turn your machines on and off. Typically in a 19th century factory, your line shafts would run all day long, and then you would turn individual machines on and off by using your counter shaft and your belt shifting mechanism, which I'll demonstrate in a minute. But if you notice here, this pulley is approximately about a 20 to 22 inch diameter, driving up to one that's about 14. So you will get a speed increase from the 200 RPM of the engine up to the first shaft, and typically line shafts in factories operated at 250 RPM. And with woodworking machinery, most woodworking machinery runs very fast. So you have to have several speed increases to get the machine up to its proper speed. First, I'll demonstrate the steam engine here. Well, if you look at your engine, you'll see that the engine is basically at the extent of its stroke. When one has a single cylinder steam engine, when it's in that position, that's referred to as top dead center, or bottom dead center, which would be the exact opposite. That would actually be bottom dead center. Now, in order for the engine to start, a single cylinder engine will not be self-starting if it is in either one of those positions. So what I'll do is I'll turn this belt and I'll get the engine off of bottom dead center, and I'll basically put it in mid-stroke. And I'll turn the steam on. Now, you'll notice when I first turn the steam on, a lot of steam will come out in the cylinder area here. Basically what that is, we're blowing the condensation. The first steam that goes into a cold engine will condense back in the water, and since water doesn't compress, you have to let it out. So when I turn the engine on, you'll see a lot of steam coming out of here, steam and water, and then we'll let it run a little bit, and then I'll shut these valves. You'll also notice that the cylinder here looks like it's made out of wood. Well, it's not actually made out of the wood. Wood is on here as a form of insulation, and it's referred to as lagging. A steam engine, unlike an internal combustion engine, like the gas engine in your car or a lawnmower, a steam engine needs to run as hot as possible. It doesn't need a cooling system like an internal combustion engine. And the other thing I'd like to mention about steam engine is a steam engine is double acting. By double acting, what I mean is the steam pushes the piston one way, and then the valve and the valve chest moves, and then it pushes the piston back. So there's pressure on the piston pushing it back and forth. Now on a, let's say the engine in your lawnmower, so a steam engine has what you'd refer to as 2 power strokes per revolution. Your engine in your lawnmower, which is a single cylinder engine, would only have 1 power stroke after every 2 revolutions. So I will turn the steam on here. Open up the valve. Now if you notice right here, you'll notice this device rotating. This is called a flyball governor. And basically what a flyball governor does is it regulates the speed of the engine. This flyball governor was invented by an Englishman named James Watt. And it was invented in the 1780s for the first truly reciprocating steam engine. And the way it works is it works on centrifugal force. When the engine is shut down, you'll notice these balls go in. That's because the speed is slowing down. So when the engine is running, these balls go out and they reach an equilibrium point between the spring pressure and centrifugal force. And that pulls a rod which controls a valve down in here. So if the engine has no load on it, if I'm running no machines, the engine runs at a constant speed. Now when I turn on the first machine, what will happen is the engine will momentarily slow down, and then the governor will instantly sense that slowing down, and these balls will react and lift the rod and allow more steam to come in. See, right now the governor is in its equilibrium point. A wood shop would have received its wood from a sawmill in the rough sawn form. If you look closely at this piece of wood, you can see the saw marks. So the first thing that would need to be done, this wood would have to be surfaced on both sides, so both sides are parallel and true and smooth. The machine used to start this process is referred to as a joiner, which I have right here. This particular joiner was made by the Gleason Company in Philadelphia in 1875. The way a joiner works is there is a cutter head in the middle. I'll turn this belt by hand, and there are two knives. And this cutter head is rotating very rapidly at 3,600 revolutions per minute. And you'll see there's a table on the inside, on the infeed, which is referred to as the infeed, and a table on the outfeed. This outfeed table is set at the same height as these knives are, and then this infeed table is adjustable up and down by turning a hand wheel. So basically what you do is you set this table for your depth of cut. I'm going to set it for about a 1/16 of an inch. And then you push your wood over this rapidly rotating cutter head, and this will produce one perfectly true surface on the side of the board facing the cutter head. Now I will turn the machine on. Now you look over here, this is what's referred to as a counter shaft. We have a belt that is currently turning a idler pulley. That is referred to as a loose pulley. This particular pulley here is a tight pulley, which is keyed to this shaft. Now, you'll see this lever here in my left hand. When I move this lever, what I will be doing is I will be shifting this particular belt from the idler pulley, otherwise known as a loose pulley, to the tight pulley, and then the machine will turn on. We'll take my piece of stock here, and we will run it over the cutter head. Now you'll see we have one perfectly smooth side on a piece of mahogany. Next thing I'll do is I will true an edge. We'll stand it up against the fence here, and now I'll shut this machine off. The next machine we need to go to is called a planer or surfacer. Since we've produced a true surface on one side, the planer will follow this surface and plane this piece of wood to a uniform thickness. Now conceivably we could just turn it over and do the other side, but what might happen is we might have a taper. One end of the board might be thicker than the other. So that's why it's necessary to use a planer and not just use this one machine. The next machine I'd like to demonstrate is a planer or surfacer. This particular machine has a patent date of 1867. However, it was made, the design of this dates from a much earlier period. This machine was made by the Richardson-Merriam Company in Worcester, Massachusetts. This 1867 patent date basically covers the method by how they oil the bearings. This particular machine is referred to as a Woodward type planer, and what makes this machine different than more modern planers that woodworkers are familiar with is the fact that the bed of the machine is stationary, and to control the thickness of the wood that you're planing, one moves the cutter head up and down through a crank mechanism on this side. Now, I'll also like to point out that this is a dog clutch here, and when this clutch lever is thrown, that turns the feed on, which makes these corrugated rollers go around and pull the wood through the machine. Basically, we have a set of corrugated rollers on one side, and the corrugations grip your wood, pull it under the cutter head, which is rotating once again very rapidly at about 3,600 RPMs. The cutter head surfaces the wood, And then on the other side, there's a smooth roller which grips the wood and continues pulling the wood through the machine. This belt right here runs a pulley and gearing to power these two feed rolls. Now we're at the business end of the planer, and if I move this dust hood back, one can see the feed rolls. This is the outside smooth feed roll. In the middle we have our cutter head, and then we have our corrugated roll here. These rolls are driven through this pulley here and some gearing. So when I turn this pulley, both feed rolls will move in unison simultaneously and propel the wood under the cutter head as it's rotating. If you look down here, this is the ball crank. By turning this ball crank, you raise the cutter head up and down to control your depth of cut. This is the feature of the early planers, which became outdated by about 1870. What I have in my hands here is an example of a mortise and tenon joint. A mortise and tenon joint is essential to any good solid wood construction, whether you're building a barn frame, cabinet door, house door, or window. As you can see, this is called the tenon, and this rectangular cavity or hole is called the mortise. And one slips inside the other and makes an extremely strong joint. Now, in the 19th century, when woodworking machinery was being developed, great importance was placed upon developing machines that could cut these joints, since cutting them by hand was very time-consuming and laborious and required a person of great skill. Now, on this end, I have a mortise laid out, and I'll just briefly demonstrate how mortises were made prior to machinery. Prior to the use of machinery, mortise would be actually chopped in using what's referred to as a mortising chisel. And if you notice, this chisel has a very stout blade. Basically what the carpenter would do is hold your chisel on your layout lines and strike it with a hammer, move it over about an 1/8 inch, strike it again, and just repeat this operation. Each time I'm striking this, I'm going in probably about 3/16 of an inch. You do this all the way across your piece of wood, then turn your chisel around, cut in the other direction. Basically, your carpenter would just go back and forth till he chopped halfway through the piece of wood, flip it over, and go through the other side. It would take approximately about 10 minutes to cut one of these joints. As you can see, it's very time-consuming. I'm standing here next to an H.B. Smith reciprocating mortiser. H.B. Smith was originally from Woodstock, Vermont, and in the early 1850s, he moved down to Massachusetts and later established a large factory in Smithville, New Jersey. Mr. Smith invented this mortiser in the early 1850s, and basically what it does is it duplicates the action of chopping a mortise by hand. This machine uses a solid chisel, which basically looks like this. The only way it differs from the hand-operated chisel, it has a groove cut in here, and what this groove does is it aids in drawing the chips out of the mortise. This mortise chisel has a tapered socket, fits in here, and this chisel, however, reciprocates at a speed of about 500 chops per minute. And Mr. Smith's basic, the single most important feature on Mr. Smith's machine is what's called his automatic chisel reverser. When I turn the machine on, you'll be able to see this in action, but I'll just give a description of it here. The operator basically puts his foot on this treadle and pushes the wood up into the reciprocating chisel. Each time the operator momentarily releases the treadle, the chisel will automatically reverse. And that's accomplished by this little leather belt here. Basically what happens is this belt is always going around, but it's slipping on this pulley. And when I momentarily release this pedal, a pin is pulled up, and this chisel goes around 180 degrees and changes its direction. So when I first start the machine, you'll see it in action. Now I'm shifting the belt from the tight pulley to the loose pulley. Now we'll watch the chisel automatically reverse. Each time I make a pass across the wood, I'm taking out approximately 3/16. Now you can see I've mortised halfway through this piece of wood. To continue the mortise, we'll flip it over. Now, if you can see, we've mortised all the way through now, both sides. Now, this took me approximately a minute or a minute and a half, and this was a great savings in time versus doing it by hand. And one of the benefits of having machinery to do something like this, it greatly lowered the cost of items, and it made it possible for people of lower incomes to have finer products.